Swayam Prabha. Digital India. Educated India.
So, how many of you are familiar with Colab, Google Colab? Okay, then fairly most of you. That's fine. So, we are using Google Colab for we will be executing some Python script mostly, and it will be ranging from executing AES, simulating power traces, and then simulating DOM, CPA, and at the end fault attack. So, we will be starting with a simple exercise like simulating AES. We will be trying to understand like about your understanding of the AES algorithm. We will also get familiar with how to execute these codes in Colab. So, were you able to download it? So, okay, so I will start. So, if you are able to download it, so if you are starting from scratch, just open Google Colab and go to this upload notebook. So, if you are going to upload notebook and then just for the initial part just select task 1 and click on open. So, if you have selected task 1, you will be able to see like it is regarding implementing AES 128. So, if you look into the code over here, so in the instruction it is written like if you see the sub operations like from line 213 to 220, just one thing like whenever this window will be appearing in front of you, if the line numbers are not there, then just go to the settings and click on this show line number thing, then you will be able to see the line numbers. So, now let us go and see what is there in line 213 to 220. So, these are the operations that are there in lines 213 to 220. These are the operations. Now, as we have mentioned in the instruction, like some of the sub operations may be missing or there may be some extra sub operations in line number 213 to 220. So, either omit them or add them to see like how to execute AES 128. So, I think you are clear with the algorithm of AES 128 as I already showed. So, just from that basic idea, see that whether you have to omit some operation, whether you have to add some operation. And then just executing the code is just click on this button. You just have to click on run cell and it will the code will get executed. So, take 5 minutes, let me know if you are able to understand it. If you are not able to understand it, we have a solution for that. So, do not worry. You do not have to study the entire code, just concentrate on this 7 or 8 lines, you will be able to understand it. So, any ideas like what line is missing or what operation is missing or if some extra operation is there?
Shift rows is missing.
Shift row is there. In the first part, right? Yeah, and then in the next part, in which line number?
Sir, in the last operation we do not do shift mix columns.
Yeah, exactly, correct. So, what you should add?
Sir, like if R&D percentage equal to cell.nr, then
Yeah, so add it up, add it in the code and execute. So, you will be able to see what is the output. So, this is what the solution is.
yes, it is printing some values.
So, if I execute it, yeah. It's fine. I think your whatever your plain text is given as random. I think if you fix the plain text, then the output will be the same, so it's fine. So there are, is this what your plain text is?
It's the same.
Is the same. So are the operations in correct order that I showed you? Did you add this add round key thing also?
Yes.
Mm-hmm.
Add round
Add round key should be there, right?
shell dot.
Add round key will be there at the end of each round, so it should be there.
Shell dot HR NR.
NR. So if you study the code, you will be able to see like all what are the purpose of all the variables. Like NR is 10, it's the total number of rounds. So
So sir, 1 to 10 is like 9 round and 1 round extra we are writing. Sir, 1 to
yeah, right. It's like 9 rounds will be normal, and then in the last round we will be just omitting the mixed column operation. Just as simple as that. So I think if you have followed the steps, your output will match. So this is the output, as you can see in the screen. So now I will be going into like how to collect the simulated traces. Before that, just a small recap of whatever sir just presented right now. Just a small recap on the CPA on AES. So the CPA on AES will be showing in two parts. One is the collection of the simulated traces, and other is will be giving you exercise on DOM and CPA both based on whatever simulated traces that we will be collecting. So this is the overall AES algorithm, AES 128-bit algorithm, and where it's a network of this add round key. There is substitution box, there is shift row, mix column, and this is the entire operation. First there is sub byte, there is shift row, mix column, add round key, and then in the last round is just sub byte, shift row, and add round key. So overall there are 10 rounds. Now if you see, this is the state matrix. As you can observe, there are 16 cells overall, and each cell there is a single byte over there. And if we give a plain text, if we give a key, we get a ciphertext. The key goes through a key scheduling algorithm in the middle. So this is the overall steps of the AES 128 algorithm. And in the sub byte operation, as I already mentioned yesterday, I think it's the transformation of all the 16 bytes based on the table, as you can see on the right hand side. Transformation from A to B, and then after that there is the shift row operation. In the shift row operation, you just shift individual rows of the state matrix in this format. Like in the first there is a single shift, then there is a double shift, and there is this A33 comes to the front, and A30 just goes to the next cell. So this is how the shift row operation works. And ideally the first row doesn't shift. So I think there will be a use of this operation too. So just remember, the first row there is no shifting. And then there is this mix column operation. In the mix column operation, each of the individual columns are being multiplied with this fixed matrix. The last round does not have the mix column. And then there is this add round key, where individual round keys that are being generated by the key scheduling algorithm are being XORed with the individual bytes of the state matrix. So now if we go on to see a single cycle of this AES algorithm from the 9th round output to the 10th round output. So the 10th round output is the ciphertext, obviously. So it goes through all these steps. Like from the 9th round output, there is this shift sub byte operation, and then there is the shift row operation, and then there is goes to the add round key operation. So this is this whole thing takes a single clock cycle on a FPGA. So we are referring to a normal FPGA implementation over here. So so overall this takes a single clock cycle. Now if we are referring to this kind of implementation, where this 9th round output, or rather what we can say the 10th round input, is being stored on some register. like be it an FPGA implementation, be it a microcontroller implementation. So these outputs are being stored onto a register. Now this storing onto the register will trigger some dynamic power consumption. Dynamic switching of data is related to some power leakage. So whenever as all of the registers are like made out of CMOS gates, this dynamic switching of data will actually leak power that will be dependent on the value of the data. So this is how, like, when we target to do CPA on an implementation, suppose we have a FPGA implementation where we have implemented AES, we generally target the 9th round where, or rather the 10th round where the data is being stored onto the register. So in this step, like the 9th round output will be stored onto a register, and then the ciphertext will be just given as the output. So the sweetest spot, like where to get the real traces, is the 10th round input, which is being stored onto the register. So at that point we will be getting the power traces, the data dependent traces, and based on that we will be performing a CPA or DOM or any attack that you need to perform. So based on this dynamic power consumption, we generally collect the EM radiation. So the EM radiation, ideally in a real setup, we have electromagnetic probes from where we collect the traces, and then the traces are being transferred to an oscilloscope. Like, it's being collected by oscilloscope, and then we collect the traces onto the PC. So this is a general working principle of a CPA. So ideally what we target over here is this, as I said, the 10th round input, and from the 10th round input we collect the traces, and then ideally we have a hypothetical power matrix and a real power matrix that we are collecting, and based on that we perform this, we compute this Pearson correlation.
So why are we using only Pearson? Have you tried other coefficients?
Other coefficient as in?
PMS.
Means
PMS coefficient.
you can try. If you can find a correlation, like it's just a metric. It's a metric that works well in order to correlate between the hypothetical power and the real power. So you can.
It depends on the data which you are getting.
Yeah, obviously. So the two data, or rather whatever power that is being animated by the FPGA, or whenever the data is being stored onto a register, that is apparently data dependent. If you collect the traces, you will be able to see, like, the 10 rounds of AES are being exactly being plotted onto the oscilloscope. So from that we just collect, or we just concentrate on the 9th round. So you will be able to see that the hypothetical power, whatever you calculate, ideally in FPGA we go for Hamming distance power model. So the Hamming distance is exactly correlated with the real power that you collect. So if you compute Pearson correlation on that, this is the exact thing that we will get.
Also, we are performing attack on the hardware part.
Exactly.
So, and we are using AES to secure the signal which is transferring.
AES is being executed on the FPGA. What is the purpose of running the AES is totally different. It can, like, maybe on a automobile chip, where suppose on a HSM you are running AES, it may be used for computing CMAC. So that's a different purpose for running AES, or maybe on a credit card, it may be used for some other purpose. AES may be executed for some other purpose. Our purpose is like the key on which the AES is being operated. We have a purpose of extracting that key.
The purpose of using the AES encryption can be arbitrary.
Can be arbitrary. It may be.
Whatever you use it for, you can capture the power, and from there you can recover it.
So whenever we will be computing the hypothetical power, so hypothetical power will be calculated in a reverse order. So suppose we will be collecting the traces based on this 9th round output. So we need to calculate the hypothetical power based on whatever the output of this 9th round was. So we will be going back, like we will be getting the ciphertext. Suppose we will be feeding the entire chip with 25,000 plaintext. Suppose we will be getting 25,000 ciphertext. Now from the ciphertext we will be going back to the ninth round. So how will be going back? We will be making key guesses, like we will be targeting a single byte. Suppose over here we target B00, suppose the first byte. So based on that we will be XORing it with the last round key, and then performing inverse, like suppose this B00 is the direct output of the first row of the shift row operation. Now the first row of the shift row operation does not go through any of the shifting, so you do not need to perform inverse shift row operation over there. You go back, so then you go back to the inverse S byte operation, substitution box operation, and then finally you end up ninth round output. So that is ideally how you go back. Okay, so just what I was telling. So if we see the cipher text over here, so if we target to get the first key byte of the last round key. So what we target is this B00 over here, this thing B00, and then we go back, we XOR it with the last round key, or the whatever the guess of our last round key is. It may be ranging from 0 to 255, and then go for the inverse shift row operation, where we do not need to perform any inverse shift row operation, as B00 does not go through any shift, as it's from the first row, and then we go for the inverse substitution box operation. So after the inverse substitution box operation, whatever we get, we collect the Hamming weight or Hamming distance based on that byte. So if we go over here, so if we are collecting Hamming weight is pretty easy to collect. You just calculate the number of ones in this B00, but if you are calculating Hamming distance, what you need to do is calculate the Hamming weight of the XOR of the 10th round first byte and the 9th round first byte. So that is how you calculate the Hamming distance. So is the difference of the positions of the number of ones between the 10th round output and the 9th round output. Based on that, you will get the correlation Pearson. If you calculate the Pearson correlation based on your real power and the hypothetical power, so you will get the targeted key byte that we are trying to extract. So now for you, there is this second task. If you upload the task 2 over here, it's regarding simulation of power traces. So ideally the prerequisite is you need to go through this, execute this part of the code, like downloading the prerequisite. Ideally it needs the aes.py file, so the aes.py file has to be there. If this somehow doesn't get downloaded, you can upload it from here. There is a zip of task2.zip. You can upload that file from here also. So that also has this aes.py. So over here we are trying to emulate the real world situation. In the real world, when you are collecting traces, like let me show you a simple setup in short. Yeah, suppose this is a basis 3 board, as you can see. It houses an Arctic 7 FPGA, and using the probe we are trying to collect the traces. So the equipment that we need for this is this oscilloscope, and there is a power amplifier. Whatever traces that we collect using this kind of electromagnetic probes, we amplify using it as a preamplifier, and then give it to directly this oscilloscope, and from the oscilloscope we collect the traces. But all of these traces are linked to some kind of noise. Like what we try to do in this experiment is we try to add some noise, we try to add some Gaussian noise to the traces that we get simulated. Like we collect the Hamming weight or the Hamming distance power model, whatever you wish for, and add some noise to it, and then try to perform CP or norm on that traces. Because
basically, very simply put, what we are trying to do is we are trying to emulate the power trace without going to the lab. Okay, so of course you can go to the lab and capture the actual power traces, but we are trying to first of all get some kind of equivalent to the power traces by this following this procedure where we add a Gaussian noise and create something which looks like the power control. Okay, and then you can on that you can try your statistical techniques. Because at the end of the day, the attack that we are trying to learn here are all statistical.
Ideally, it takes like, in order to collect a trace, it takes a whole day. Like we have to collect around 25,000 traces for a single run of, or 25,000 runs of the AES on a FPGA. So it takes a whole day to collect the traces, and based on that, you ideally, in order to perform CPA in a real life experiment, we see that we need around 4,000 traces. If 4,000, if your probe is good. If your probe is noisy, you need around 10,000 traces in order to perform a successful CPA. But the purpose of this whole experiment is to see, like, as you add noise onto the traces, how you have to increase your number of observation in order to extract the correct key byte. So over here you can see, like, we have given some parameters, like if there is this noise equals to true or false, you can say, you can change it to either Hamming weight or Hamming distance model. The parameters you can tweak based on that, like we have given this assignment based on that. So over here you need to complete these lines, like, yeah, suppose how to compute this Hamming weight, yeah, how to compute this Hamming weight noisy. So I will be not going into like how to solve this, I think you can figure it out. I will just going into like how the solution looks like rather. So let me directly go into the CPA experiment. So we will get a more clarity from that.
Which Python file should we find in the task2 repository?
Task2 is there. The name is only task2. See,
In the collab, you told that if that file is not present in your
there is a task2.zip. Is it there? Not here. In the folder that I have given you. The drive that I go into the drive. Is it there?
From drive, you can directly go to the So we don't need to download the task. We can go directly from the drive.
Yeah, that is fine. But suppose if you are not getting the prerequisites, you will not be able to execute the codes. That's the issue. So is there any doubt regarding how to collect the simulated traces? Shall I show the demo? Okay. Let me show you the.
So in task2, what do we need to do? In task2, what do we need to do?
You are given some lines where you need to fill the code over there.
So they evaluator mode.
There is something called your code. You need to write that code.
Let me show you.
You will see that there are certain missing lines.
See, yeah, there are certain missing lines over here. You just need to fill those.
But I think we will show you the actual code.
We will show you the actual code because you need time to solve them. So I will be showing you from the main file. So over here we are collecting around. So if you can see the simulation length that we have chosen over here.
zip में फाइल है AES
Dot py.
हाँ तो ये task2 का पूरा आपने अपलोड किया IPython फाइल तो ये AES.py किधर अपलोड करें?
See, there is something known as the prerequisites. There are two options. Option 1, download the prerequisite. So if you directly click on this, if it works, then it's fine. If it does not work, there is option to upload the file. Just upload the task2.zip. And so over here, based on the parameters that we are selecting a length of 5,000. Like we will be going on to simulate, we will be giving 5,000 random plain text to the AES algorithm, and we will be getting 5,000 ciphertext, and this is the simulation length. For now, we are selecting Hamming distance HD, like we will collecting the traces based on the Hamming distance power model. We are giving some noise, we are adding some noise, that's why we have placed it true. Now I will be showing you like how the noise is being added. Okay. zoom it, it will be, wait, is it fine now? So Hamming distance power model, noise we have chosen is true. So based on this, this part of this function will be executed, power simulate Hamming distance. So if we go on to this function, this encrypt power trace HD will be executed. Yeah. So if you look into this, whenever this encrypt power trace HD will be executed, ideally what we do is we execute the whole of AES, and in the middle we try to collect the, see over here we have chosen a plain text, like ideally this is the initial plain text that we will be choosing, and then after that we have started executing the whole of AES. As you can see, like this is the initial state, and then we do this key whitening step, like the initial add round key we generate, and then from this part we ideally what we say, we collect traces from 12 points. Now there are 10 rounds of AES, so then where from these 12 rounds come from? So ideally what happens is, initially the plain text is being loaded, and then there is an initial add round key, this is the second point, and then there are 10 rounds of AES. So ideally what we say, so there are 12 points from where we collect the simulated traces. So this is exactly what happens in original situation also, like whenever we are collecting traces from an FPGA, whenever or any other device, be it a microcontroller, be it an ASIC. So over there also there is a loading of plain text, there is a loading of this key, and then there are 10 rounds of AES. So there are ideally 12 points that we will be concentrating upon. So over here also, see whenever the plain text is loaded, we compute the power based on the Hamming distance. Now after this initial add round key, again we are calculating the Hamming distance power model, and then after each round of AES, as you can see, we are checking like whether we need a noisy trace or a normal trace. Based on that, we are computing the Hamming distance, like we are sending the previous state matrix and the current ciphertext matrix in order to calculate the Hamming distance, and based on that we will be collecting the computing the power trace. So what is going on within this compute HD function is just taking in the previous state and the current state, is doing a XOR and calculating the Hamming weight of that XOR. That is the power value that is being calculated, or rather the simulated power value that is being calculated. If you are trying to add a noise to that, so we are computing a random noise, like this random normal is the Gaussian noise that we are trying to sample from a Gaussian distribution, and adding this noise, we are adding this S to the Hamming distance value that we are computing in each step. So this is how we are ideally calculating this simulated power. So the solution is the code is being given to you. You can do the solution based on what we have shown now. Now suppose we are going for CPA. CPA is in task 3, that the files we have given. So if we are trying to execute CPA, you will be able to see like the difference. Okay. So in the CPA code also you are given some parts where you need to fill in some of the blanks, where like these are the parts that you need to fill. So I have already shown you like okay. So the prerequisites are downloaded. Now in the CPA, if we go into like the coding part over here, let me show you the parameters that we are choosing. So initially let's go with 400 traces. So we have collected 5000 traces in the simulated power trace section. So now based on that we can choose like how many observations do we need in order to compute the actual key, or how many number of observations that we need to give to the CPI algorithm. So let us start with 400 traces. Now we can go for the Hamming weight leakage model or the Hamming distance leakage model, whichever you choose to. Initially we are going for the Hamming weight leakage model. Then we are trying to choose the target byte. So target byte, as in the PPT I showed, we are going for B00. So we are going for the initial or the first byte. You can change it based on that, the code will adapt to it. So then we have this num row and num column, where num row is 256. 256 as in we have 256 key guesses like 0 to 255, and WLEN over here what we choose as 12. As I said that there are 12 points where we will be collecting the simulated traces. So number of columns is 12, so and the number of rows will be 5000. We will be collecting the simulated traces, and out of that now we will be using 400 of them. Another thing is like choosing the file. So initially, so let's not choose noisy initially. So we will be choosing normal Hamming weight based simulated traces. So if you are choosing 400, so ideally the correct key byte should be D0. So let's see whether D0 comes or not. Yeah, D0, this is the correct key byte that we got. So over here if you see like this is the CPA plot. So as I mentioned, like for D0 we are getting the maximum correlation, and this is the correlation value that we have plotted over here. So ideally what we do over here is we are not concentrating only on the 9th round, but other than we are concentrating on all the 12 points, all the rounds we are concentrating on. So we are correlating 256 cases with all the 12 rounds and trying to extract with which round we are getting the maximum correlation. So but if you know that you are targeting the 9th round, and ideally it is quite difficult to select from the original trace like where the 9th round is occurring, because we from the oscilloscope that we are choosing, if it has a high sampling rate we will get like 100 k points from that at the same time. From that 100 k points you have to choose where the 9th round is occurring, and from that much amount of length we will be able to perform the CPA. So ideally it is quite difficult. So over here we are getting only 12 points, but ideally in original situation it is not like that. So we will get more number of samples.
So it will be computationally.
It will be, yeah. So ideally if you go on and see the traces in the oscilloscope, you will be able to choose the point where you need to do. So if you zoom in, if you set the pointer ideally at certain places, we will be able to choose the exact point where you need to perform the CPA. So that's a tricky task. No, no, tell it.
So at the end we want to maximize the likelihood, right?
Yeah.
The noisy one
Yeah.
should be, we want to maximize the likelihood between noisy one and original.
Noisy one and
Original one, right?
original one I did not get. There is only the hypothetical one and there is the original trace.
Original trace and the hypothetical. So here what we are doing, we are calculating and then we are approximating. And then
You are first approximating and then correlating.
on the basis of correlation we are saying that the likelihood is maximum.
Yeah.
So rather than that, why not choose Jensen and entropy? Entropy based method.
Entropy based method as in?
There is a method called JS entropy.
I did not get. Like, can you expand what you are trying to do?
Okay, so I think your question we will take offline. Let's try to understand this method. I will talk about mutual information and all.
There are other methods also. Like what you are trying to do is there are template based attacks, there is mutual information based attack. Like other than CPA, there are 1,000 kinds of attacks that you can perform. So this is just a kind.
If you want to drive, right, you just learn to drive on an ambassador. Once you learn,
So this is just the initial kind. So there are.
learn one car first.
So if you are trying to perform templates based attack, there are MI based attacks also. So mutual information, the entropy that you are trying to say, but that does not apply over here. This is just the correlation based power attack that we are trying to perform. So now if I change the file to noisy one, so I have kept the number of observations to 400 and changed the file to noisy. It was not able to extract the correct key byte.
See the effect of noise actually.
So now if I go on and
So
increase,
all of you see this, right? I mean, that you can't distinguish now because the red is now merged in the black lines actually. Okay, so you cannot. That's the effect of noise.
so now you need to increase the number of traces, number of observations rather. So it was 400. So ideally you can increase it to 500, 600. You can see the effect. Ideally, almost if you do it 1,000, it ideally matches. It should.
So in a real life experiment, you will do it incrementally. So you start with 500 to 600.
So ideally, in a real life experiment, when you're collecting traces using EM probe, yeah. So
So now it again stands out.
now it stands out again. So using a real probe, what you will get ideally, like you need at least 4,000 traces, even with the least amount of noise. So this is the basic of the CPA attack. So we can stop here.